Okay, so I want to give you the divergence theorem quick in its full glory.
And then you're going to tell us how the book cheated?
Yeah, I'm probably going to mention how the book cheated. So the divergence theorem says if S is a smooth, and really you could add piecewise smooth, surface bounding a region D, let me see, and F is a smooth vector field. That sentence maybe doesn't make much sense.
It just means continuous.
Yeah, that just means the partials are continuous. And the partials better be continuous, right? Because you're going to take the divergence of this thing. So if you're taking a divergence and you get a discontinuous function, probably there's something really, really broken, right? And that's why we shouldn't allow you to do this. So we have S, a smooth surface bounding a region D, and F is a smooth vector field. All of this should be taking place in R3, although it doesn't matter so much. No, we should let's leave this in R3. Okay. And what else did I need?
That they're all outward or inward, that they're all.
Yeah, I need that thing to be oriented outward. Yeah, and that's kind of where they cheated, is outward orientated. I don't know how you spell oriented anymore. I lost it. Don't worry about it. Okay? So if all this, then what did we discover just a minute ago? Then the theorem.
Yep.
Then the integral over S of, wait, this is a surface integral, right? So what's this guy going to be? This is going to be f dA, because this is a surface integral, right? In other words, the flux through S, right, is
To the integral D of D.
yeah, so this should be a triple integral, right?
Yeah.
So I'm going to use good notation. I'm going to write integral over D of what? Divergence of F D volume. You guys cool with that?
Yep.
What was the cheat?
So the book cheated. They didn't write. So they wrote if S is a piecewise smooth surface bounding a region D, and F is a smooth vector field, and S is outward oriented, then this, right? So there's one little thing they cheated with in there, which is
it orientable at all?
yeah. So they sort of assumed it was orientable when they told you it was outward oriented.
So they did both of those in one little step, basically.
Yeah. You guys see that?
It's implied.
Yeah, it's sort of implied. And keep in mind, this only works, right? It only works when you have a smooth surface actually bounding a region. You guys see that? This will not help you do fluxes through graphs, for instance, right? Because graphs necessarily pass the vertical line test, and thus they do not have a bond. You guys see that? This thing actually needs to enclose something. So you can do fluxes through spheres with this, right? You can do fluxes through cubes, right? As long as all the sides are included and they're all oriented the right way.
Yep.
So can you do flux through like, what was that problem we did earlier? There was a graph above this certain rectangle.
Good question. So the graph above a rectangle is going to look like this, right?
If it happens to be bounded by the rectangle, I guess that's what I meant.
Yeah, so if you put and the region underneath it to the XY plane with all the planes bounding it, then maybe. So this thing, as phrased, like the flux through the graph over a rectangle, no. But you could add those sticks, right?
Yep. And they
So
keep that.
if you had something like this, where you had all of these things added in here and you actually meant, right,
This entire,
all of this volume, right, so your surface is not just the top, but also the bottom and all four sides, then yes. But just the top, no, not gonna happen.
And that would just affect your limits of integration, right?
Yeah, so that'll change the limits, right? In the other one, like, you'd try to if you just had the graph, right, you'd go, okay, so I'm going to take that, I'm going to turn it into a volume. Shit. What is closed up in here?
yeah, it's like
Right, if it doesn't enclose anything, you can't say the flux through the edges, right? Because there's
yeah, because when you do
there's no inside to even talk about the edges for.
if you did like d-volume, you basically get one of your integrals from 0 to the limit as it approaches 0. Or like,
Yeah, so what you could do, right, is you could do something like this and then like slim up the difference between the two or something, but that would be major overkill for calculating this.
yeah, there's probably better ways of.
Yeah,
Like
do
just
this.
doing a normal
Like
Yeah.
you guys know how to parameterize the surface. So that the cool thing you can use this for, there's one neat thing. If you start with a region that's 5 sides of a cube, you can use the divergence theorem to flip that to one side of the cube.
Oh, say that again or something?
Yeah, can you?
Yeah.
Yeah, let me shut this off.